Hey everyone, my name is Vanessa Callejas. Welcome to the meeting. We're going to do a quick audio check just in case there are folks who are struggling. Can everyone hear me?
Yes, I can. Yep.
Perfect.
Yes.
Yeah. And if during the call you have any problems, you can just chat with Katie or I directly. And let us know. Okay, the meeting is being recorded. We're doing it mainly for note-taking purposes because my colleague Katie Johnson will be taking some notes. And we're also going to be putting together a video that will be shared out on with a short little title card and et cetera, just so that the folks who couldn't attend will be able to see the discussion and see what good things we've gotten up to here today.
Yeah, I think Steve Cooper and some of the Federal Highway people are at a conference, so that he asked if we could record it, which I think is a good idea.
And we'll share it on your MnDOT YouTube channel.
Yep.
Perfect. The meeting's going to be about 3 hours with 2 breaks, and I'll be tracking the chat as well. So depending on how many people join, if you feel more comfortable asking questions via chat, I'll bring those chat questions up to Kyle and the presenters as they come in. So our first step would be to do a quick roll call. Just tell us your name, your role, your agency or organization that you're associated with. And I'll start with, let's see, Kyle.
All right. Thanks, Vanessa. So I'm Kyle Hoig. I'm the project manager for the DPS pooled fund. And this is part of our pooled fund activities, is to have these almost quarterly technical working group meetings. This is actually our first full-fledged meeting. Some of you, or most of you, were probably at our kickoff meeting earlier this year. And I work for MnDOT in the research department.
Thanks, Kyle. Over to Richard.
If you're referring to Rich Hamilton, that's me from New York, Advanced Testing. We're a construction materials testing firm, and we've been using the DPS technology for the last 3 years.
Thanks, Richard. Roger Roberts. You're on mute.
Roger Roberts from GSSI. I work with the CaveScan products and have been working with it for the last 5 years.
Thanks, Roger. John Stork.
I'm John Stork from North Dakota. I work in the Materials and Research Division. I'd be the main operator of our DPS system here.
Thanks, John. Rob Sommerfeld.
Rob Sommerfeld. I work at GSSI as well. I sell and kind of consult on the product with GPS, work closely with Roger.
Mike Johnson.
Yeah, hi, good morning. My name is Michael Johnson. I work with MnDOT. I'm in the materials lab that Kyle and I and Mercedes and some other folks maybe are on this call. Same building, different unit. Been focusing mostly on intelligent compaction, paper mount, thermal profiling, and starting to get more into the material delivery management system, e-ticketing. So.
Thanks, Mike. Larry Riggleman.
Hi, Larry Riggleman. I'm the asphalt field engineer for Maryland Department of Transportation.
Thanks, Larry. Karen Carley.
Good morning, I'm Karen Carley. I'm the State Pavement Design Engineer with the Washington DOT.
Thanks, Karen. Rebecca.
Yes, I'm Rebecca Embacher. I work with the Minnesota Department of Transportation in the Advanced Materials and Technology Unit.
Thanks, Rebecca. Robert Hinman.
Hinman, a pavement materials engineer with the Federal Highway Administration out of the Ohio Division Office.
Thanks, Robert. Jonathan Varner.
John Varner, pavement engineer with Missouri DOT.
Jean-Tao Dai.
Yeah, thanks, Vanessa. I'm Xiong Tao Dai. I'm a research operations engineer at the Minnesota Department of Transportation. I work with Kyle on this DPS pool fund study.
Thanks, Dai. George Chang.
I'm George Chen with the Transit Group. We're working with the NWRA pool fund study with Rebecca to develop a map-based software called Veda for intelligent compaction, paver mounted thermal profiling, and DPS, and also the material delivery management system.
Thanks, George. Mercedes.
Hi, I'm Mercedes. I work with MnDOT, and Kyle Hoig is part of the DPS operations pooled fund crew.
Thanks, Mercedes. Amanda.
Hi, I'm Amanda Gilliland, and I am with the TransTech Group.
Thanks, Amanda. Grant Courtney.
Hi, I'm Grant. I'm a student worker under Kyle Hoig and Mercedes.
Thanks, Grant. Abbas.
Abbas Tayavi from TransTech Group.
Thanks. Ulrich. I can't quite hear you. I'm going to skip Ulrich and go to Jacob Walker.
I'm Jacob Walker with Georgia DOT. I work, I'm the supervisor in our technical assistance engineering unit and leading Georgia's effort to evaluate the RDM.
Wonderful. Ulrich, do you have audio now?
Can you hear me now?
Yes, perfect.
Okay, sorry about that. I'm Ulrich Kamusugenu. I work with the main Department of Transportation in the Research and Innovation Office.
Thank you. Craig.
Hi, this is Craig Blondefeld. I'm with the Ohio DOT. I'm an administrator for our Office of Pavement Engineering here at ODOT.
Thanks, Craig. Irvin.
Hello, Irv Ducats, Flyer ELD Consulting, retired contractor, work with the Minnesota DOT and other companies in implementing DPS, and also planning a TRB workshop on DPS this year.
Great.
Welcome to be here.
Thank you. Rich.
Hi, this is Rich Giesel. I'm the state quality assurance engineer for Alaska DOT. Good to see so many friends here.
Thanks, Rich. I'll introduce the CTC group. Katie, go ahead.
I'm Katie Johnson, and I'll be taking notes today.
Thanks, Katie. And Brian.
And I'm Brian Hurt with CTC and Associates. And if and when this group meets in person again, might have a chance to meet you all there. Thank you.
Thanks, Brian. Myself, Vanessa, and I'm the main point of contact with CTC, and my role here is to support MnDOT with their DPS pool fund communication needs. And over to you, Kyle.
Well, thank you very much. I'm excited for this event. I think it'll be good to have this group together to discuss some of our, I guess, major topics that we identified in the last kickoff technical working group meeting. So I wanted to, first of all, can you see my screen? It should show the agenda right now.
Yep.
Okay. I wanted to just briefly go over, I guess, the main purpose of the group. Just a quick reminder that our goal is to work as a group of density profiling system users and technical experts to identify barriers and work towards solutions for deployment of the DPS method as an asphalt pavement compaction process control and/or density acceptance tool. And the last kickoff meeting, we did a pretty neat, I guess, polling exercise that CTC set up for us and identified these 4 topics, and then subsequently have identified champions. So I'll be championing, along with George Chang and Craig Landefeld, the data analysis topic. Fabricio Leva from NCAT will be championing our precision bias and other topics. Topic number 2. Topic 3, Rich Giesel is our champion, and he's working with Dennis Dvorak and Robert Hinman. And then I'm getting a little bit of noise from somebody. Okay, it's done. And then topic 4 is limitations, risk, research needs, strengths, weaknesses, opportunities, threats, and that'll be Robert Hinman championing that along with Harold Von Quintus and myself. So with that, I guess we could quickly open the recap from the previous meeting here. Let's see here. So a similar attendance to what we have today, I think around 30 or so of us. And we basically developed our purpose and identified, we had a couple presentations that Robert Hinman and I will be updating today. But then the main point was identifying those 4 topics that I just shared with you. And then we came up with this meeting format where we're going to be kind of focusing on specific topics with a presentation and discussion. And we'll discuss how that's working at the end of this meeting to see how we want to move forward to try to advance the technology. So with that, I think we'll get into the presentations, and we're going to focus on topic 1 here initially, and that'll be myself, and then also Mike Johnson from Rebecca Embacher's group here will be also presenting as part of this topic. Okay, can you see my slide?
Yes.
Okay, so just to start with, before we get into some of the more advanced analysis that Mike Johnson is going to show, I wanted to first give an overview of kind of the meat and potatoes of what we're trying to accomplish with DPS technology. And really, it's pretty simple. We want a full coverage map of the placed asphalt density map. And that can look similar to what we have here, which is a representation of the data in Veda or a Google KMZ file that is automatically created by the device each time you collect the data. But this is really what it boils down to, is taking this device that measures dielectric continuously behind the final roller compactor and creating a map that gives us information about the density both across the width of the mat and then, of course, longitudinally throughout the day. So with that, Mike's going to get into some examples on this specific project and talk about how it ties in with some of the other intelligent construction technologies. This is just an example with where paver stops manifest themselves in lower density locations, and then also looking a little more detailed at how the variations of temperatures throughout the mat, for example, can affect our density, but we're not going to go into detail of that yet. So one thing that's just critical for this technology is training. And this on-site analysis is something that could be very powerful for the use of this technology as a process control tool. So I just wanted to give this group an example of one of the first projects we were on this year, training in a contractor and what to look for on the project and how this type of technology can be used with the on-site feedback. And like I said, then we'll go into a little bit more detailed examples later. So what we've asked for as a group is the ability to take this technology and convert it to information that engineers are used to looking at when we're evaluating the asphalt placed mat density. And one of those tools that's been developed with this technology is just a simple way of categorizing the data so we can get a percent conforming result, and we can get it real time when we're out there collecting the data. So the long story short here with this slide is that if you set the limits for what you find acceptable for density at your mat and your joint, and you define what is considered joint data and what is considered mat data, as well as your lane extents, you can just generate these tables that can be plotted that give you basically your percent conformance over whatever segment length you want to see them. And that is both for the mat and the joint throughout the project. And I just wanted to go through one example of how this type of information can be used. So this percent conformance information, like I said, it can be categorized by mat or joint. And at the beginning of the day, you'll see here, we're seeing a little bit lower than we'd like to see density on the right side of the longitudinal joint. And one way we plot this is we give both, on the left side, you see just your average percent compaction for both the mat and the joint versus stationing. But then more importantly, in my opinion, is what percentage of the mat and the joint is actually conforming to our standards for for density. And you see down around 10-20% in some cases here at the beginning of the day, around stations 83 through 86 especially, we're getting really low percent conformance at the joint. And of course, you can also map this geospatially and see visually these low spots at the beginning of the day. And if you zoom in, you can see, so here is the actual center line, and this is on the right of center looking up station, this line of data that we're seeing lower than we want to see for our percent conforming, and then also, of course, our percent GMM density in those locations. So now let's move forward a little bit towards the end of the day and look a little bit at that data. So this is the data that we started to see towards the end of the day, and this is what we want to see with more a higher percentage of our joint conforming to our standards for what we consider to be acceptable. So the question is, what changed? And one thing that I'll be pointing out here is that yes, we can do these fancy maps and do our analysis after the fact, but some of this information is just readily available right away when you get out there with the technology. So this is Doug. He's the contractor, his first day on the job, and we hired him to push the cart for us. And basically what we told Doug at the beginning of the day is you get these 3 squiggly lines that are associated with your sensors here. If you see one of these squiggly lines drop below the other 2 squiggly lines, take a look at what sensor that is and realize that that's actually corresponding to a drop in density. So this is actually the sensor that was showing these lower density spots corresponding to the measurement close to the longitudinal joint in the right lane. And this is echelon paving too. So this is not something that we want to see. So sure enough, the foreman came driving up and asking us, how are we doing today? How's our density looking? And we explained to him that it looks really good, except for this spot on the right side of the longitudinal joint, and explained to them, you know, the data we're seeing coming in on the tablet, and they took off and started talking to their breakdown roller and looking at their operation, and in this case I think maybe bridging across the lanes was causing that low spot. But from our point of view, we don't really care what they changed from their operation. What we care as an agency is that they were changing from this here, which is a really good mat except for that specific location, to fixing even this spot that was showing us low density on the right lane, right side of the joint on echelon paving. And that's just a small sample or a small change, but you can see here this makes a huge difference on the percent conforming. And then of course I would argue this makes a huge difference on how long that pavement is going to last, and who knows if and when that change would have been made without this type of technology that's readily available. So, and just before we move on to the more kind of complicated analysis, this is just an example by the middle of the day. This is Doug moving along the shoulder now, and seeing the squiggly line drop towards the joint on the shoulder, and this is his first day on the job, mind you, and he's already pointing out, okay, this is a spot where clearly the roller compactor must have been riding up on this existing pavement, or something was going wrong with their process to have this kind of a drop in density. And this is something, again, that a first-time user of this technology can readily identify with this technology. So that's something that I wanted to emphasize with the value of this type of technology, and getting it in the hands of contractors and trying to use it to improve our operations. So Mike, we're going to introduce here now to give us a little bit more detailed analysis, and this is more stuff that we can do after the fact. So this is looking at a project where I saw lower density, again, a pretty good project overall, but I started to see some lower density here, and then specifically in this area starting at around station 141. So I video chatted Mike, and we happened to be wearing the same shirt that day, which was just an added bonus. So I had to get a screenshot of that conversation. But basically I asked Mike, I said, you know, what's going on here? Why is the density lower around station 141? And of course he pulls up his other intelligent construction technology information in Veda, and sure enough, a paver stop of 50 minutes is occurring at around 141.50. And of course you got your corresponding cold mix there. And looking further into this data, you can actually see in addition to this 55-minute paver stop in the other lane, a little 2-minute stop, and then a 49-minute stop. Well, sure enough, that also corresponds to the other issue we had with low density, down below 90% GMM, all the way across the joint here, corresponding with this paver stop, and all the way across, all the way across the lane in both lanes, corresponding to these paver stops. It can be further broken down to the temperature at the breakdown roller, where here you see the low temperatures by the time the final roller, this is not something you want to see by the time actually the breakdown roller got there, and this is of course what we get when that happens in terms of low density occurring when we have a low temperature at the breakdown rollers. So I want to thank you for your time with my presentation here, and then hand it over to Mike to talk a little bit more about the use of Veda, and then we'll bring everything together with DPS and Veda after that. So I'm going to stop sharing my screen now and hand it over to you, Mike.
Okay, so I have a PowerPoint. So we've been using intelligent compaction, paver mount thermal profiling. We've been at full deployment for 4-ish years. And since we've been using these technologies for quite a while, we've been able to identify cases of lower densities. And then we'll tie this into the dielectric profiling system data here. So again, during the intros, I think George did a quick little intro on Veda, but I'll just briefly touch on this as well. So originally we had several different intelligent construction technologies with a number of different vendors. So there was a need for one system to see all this data. Veda became that system, and it's a standardized platform for viewing and analyzing geospatial data with maps, filters, sublots, spot tests, and some analysis. And I'm going to show you all those things here after the PowerPoint. And so we have a bit of a roadway here, a schematic for intelligent construction technologies in Veda. Up here on the top is a number of technologies. So on the left in yellow is technologies that are currently in Veda. Green are ones that are funded and under contract and should hopefully be available in Veda here in the next year or so. Red technologies we have funding approved but are not under contract, and there's one star under the identifying the ground penetrating radar that is going to be the next one to move under contract. So, and then we have a few other technologies that we don't have fully funded, and this is I guess this is the good opportunity to say that this Veda software has been developed with a pooled fund, and it's tied in with the NRRA. And if you want to be a part of that process and help move some of these technologies and or identify other technologies, please consider talking to some NRRA folks about it. So, okay, so the Veda software, what we have on the left here is as I mentioned before, we have several technologies, the same colored bubbles. As long as that data is in the AASHTO MP39 format, or there's an API that's put together, it can go into Veda, and then we can view and do all the analysis on those technologies. And then under contract, I believe was on the previous slide, this is going to get tied to AASHTOware, which then we would have information going back and forth from AASHTOware to Veda with pay items, mixed designs, lab results, all those things. And then there's also a route up here on the top for non-AASHTOware users where that same information can be brought in and out. And then also just an FYI here at the very bottom of this schematic is the Veda software is in the process of turning into more of a web-based platform instead of a desktop version. So we will eventually be able to see these technologies more real time and out in the field and can react to it quicker. So this is just, you've seen some screenshots from Kyle's presentation. Several of them were from Veda. And this is just another example here. As I had mentioned before, paver mount thermal profiling and intelligent compaction are already technologies in the Veda software. So paver mount thermal profiling is in the middle, intelligent compactions here at the bottom, and then at the top, we're in the process of funding the material delivery management system. And sorry if I didn't explain it before, but that's the expanded version of e-ticketing. So once that's all in there, then we have an opportunity to track the trucks, and it'll be a lot easier to identify changes in mix design. And sorry, just got a couple notes here. Dump locations, and we can identify, the moments when we need to adjust calibration curves, which is related to the DPS system. So this, having these other technologies in here will help you identify and also organize your DPS data here. So I'm going to jump into some examples that we've found over the years for intelligent compaction, paver mount thermal profiling issues we've identified with low density. So, and I'm going to try and get through these fairly quick here, but so what we have here at the top is paver mount thermal profiling data. And then, so the red is kind of the higher temperatures and the green is slightly lower temperatures. And what we have is each time there's an incident of green data, that same information is down below here in a time paver stop situation. So there's, each time there was the cooler green data, it lined up with truck stops and a paver stop of, as you can see on the screen, anywhere from 20 to 55 minutes. So we've been recommending for quite a while that contractors use a pickup machine or something to remix the material. And that same project, they grabbed a pickup machine and those paver stops became less of an issue. And then you could see this significantly less variability in the paver mount thermal profiling data up top. And then the much shorter paver stop times. In this example, there's only, the worst one was 10 minutes. You can kind of see the difference. So touching on this, I mean, most paver stops are preventable with changes to the operation. Those paver stops negatively affect durability, density to ride, and everything else. So, kind of the goal is to reduce or minimize the paver stops, and just here at the bottom, there's, here's a perfect example of, you could see darker green and even blue colors here at the bottom, and the circles with the number next to them are indicating paver stops, and that's the duration of the paver stop time. And there's a, right in the middle is a 23-minute paver stop, but you could see even 2 or 3 and 5-minute paver stops have a change in color. So we were able to identify some instances where we had increase in localized area roughness with our profile data, and then we went back and looked at our paver mount thermal profiling data, and we're able to line up almost perfectly some paver stops. So those were lining up in that instance, depending on the contractor's operation. Sometimes those are apparent and sometimes they're not. So just indicating that. So it's not obvious out in the field when you will get an area of increased roughness or not. So other issues we've seen is windrows not overlapping. So you could see a picture here of, they dumped and there's a big gap in the middle, and then what happened is cooler material that was in the hopper came through, and then you can see on the screen moments later that there was a significant drop in temperature for the material. And this is out in the field. This screen is on the back of the paver, so a paver operator can see that impact occurring in real time. Other issues we've identified is some high temperature hotspot areas. So here we can see there must have been to change the plant because our temperatures are a lot higher, and we can see in the Veda software, not only can you view it, but you can right click and search it, and I'll show that example. And in this example, we right click and searched, and there was 350-degree asphalt, which is, I'm guessing the binder probably didn't like that as much. So probably not going to perform as well long term. Cold weather compaction. So we had other instances where you can see in the picture here at the top that one lane is kind of more of the uniform pavement that you normally see, and then the other lane, you could see that, I mean, the aggregate's exposed and it's not continuous. Not the continuous surface that you normally see. So we looked at this data with the intelligent compaction paver mount thermal profiling data, and we can see here in this 2 screen here in the bottom, the top one's the paver mount thermal profiling. We don't have the legend, but you can see the blue indicates cooler compared to the green. And then down below that is the breakdown roller temperature, which also indicated some cooler material there, just verified by the temperature sensors on the compactors. So other issues we identified is segregation under the gearbox. So as that material is fed through the paver, it goes down 2 slot conveyors, and then the gearbox pushes it out in front of the screed. And what you see is that there's this strip of cooler material that ends up sitting right there at the center where the gearbox is. And so this screenshot just shows you right down the middle, there's a strip of cooler material. We also get segregation under the slack conveyors. So you could, in this instance, it's a little bit easier to see on the left example, but there's, and if you see out in the field, if you lined up those 2 lines, they line up perfectly with the slack conveyors. So there's some issues with the operation of the paver that's showing up here in this paver mount thermal profiling data. And then the other example here, just same information, but 2 lanes combined, same process. So other instances we've identified is trucks driving over the windrows. So it pushes that material down, the pickup machine can't pick it up as well, and then you don't get some cool material mixes or gets paved over, so you don't get the full thickness of the lift. And then what happens is that you get some cooler material show up here in the mat. So folding of paver wings, we see this. I've seen it driving down the roads a number of times. So what happens is cooler material collects on the side of the hopper. At the end of a load or a dump, they'll fold the wings. That colder material will go through the paver, and it'll turn into this V shape in the thermal data, as you can see the zoomed in version on the right, and then just overall on the left. And then they may be visible, and then you could even see the picture with the zoomed in picture with a quarter where you could see the aggregate. So rain events, we've seen a lot of you get a rain event and all of a sudden the material cools down, and then it's just significantly cooler than what the other loads were happening. That's just a quick example here. Similar deal, this is a rain happened overnight, and then a stockpile got saturated. And then at the plant, they just picked up that saturated stockpile and sent it through the plant, and that saturated aggregate just did not warm up and did not make it to the site at a reasonable temperature. So some more examples here. More on the intelligent compaction side. So the top screen is the breakdown roller, and the average temperature is 235 degrees. then the intermediate roller 185, and the finished roller 125. So these, you could see the big drop in temperatures between the roller train and what happens when you don't get compaction occurring in the proper temperature ranges. We had lower density on the mat, and this contractor had a disincentive for their densities. So other issues we've seen, there was random failing cores. So on the top here, the screenshot on the top is where the breakdown roller was and where they rolled. So they rolled everywhere and within the lane. But when we switch to other instruments on that intelligent construction roller, one is the stiffness values we're receiving. In this instance, it's in CMV is the units. And what happened is these areas where there's no color indicates there was no vibratory compaction occurring. So as the roller was compacting, they'd turn off the vibes and roll off, and then they'd roll back on and turn the vibration back on. And what happened is these areas never got hit with vibration, and they corresponded with some failing cores. So other issues we've observed is just the rolling operation itself. So with this system, there is a screen that the operator can see, and they can see where they've rolled. It's instantaneously mapped. But prior to that, these contractors, an operator would, they'd start compacting and they'd go until they see the first tumbleweed, and they'd stop and go back to another preset area and back and forth. And over time they miss areas. And you could see that this example here on the top is the number of passes that this breakdown roller had. And there's a number of areas where, especially towards center line, where there was only one pass by the breakdown roller. So going to be challenging to get density when there's only one pass from the breakdown roller. Other examples we've had, so up in the top left is some asphalt that failed, and that was, I don't know if it was the same season or right away after spring, but it was fairly immediate. Well, I guess there's no striping there, so it was immediately after construction. This asphalt just started failing, and what you could see with this Veda software is you can turn on the aerial map, and you could see that this road went through a boggy marsh area. And then again, based off of the legend on the top right, this Trimble CMV is a stiffness value. So there was significantly lower stiffness values in this stretch, and that corresponds to the failure area. Other issues, vibration, vibratory compaction that didn't occur along the joints. So on the left, we could see that, roller had plenty of passes in this area, but on the right, again, not getting the vibratory compaction, which happened to be where the cores are falling. And then I think Kyle kind of had some of these similar screenshots here, but basically, paver stop at the top and then lower density on the dielectric profiling system here in the bottom. And that reoccurred over and over. I think Kyle had this screenshot. So, and then Kyle had a zoomed in version of this left one right here as well. So I think that's just about the end. Again, more connections of paver mount thermal profiling data, and then lower density in the dielectric profiling system. So let me bring over my Veda software. So haven't been paying attention to the time, but here hopefully in 10 or 15 minutes before this Zoom meeting gets cut off again. So this is one of the projects.
Well, hey, Mike, actually, we're back in business with the Zoom meeting.
Oh,
so we
okay.
don't have to worry about that anymore. So.
Okay, well, that's great news. So.
Yep.
All right. So this is the Veda software. This is one of the projects where we had intelligent compaction, paver mount thermal profiling, and either Kyle or someone on his team, or even they hired out a contractor to collect DPS data here. So this is in the beta software. There's all sorts of other classes and training that TransTech Group can provide about creating these filters and taking care of the data and importing it all. You know, there's a number of steps to get to this process is all I'm saying. But right now, currently what we're looking at, just bring your attention to the top right here, this legend, we have just pure dielectric data. I can switch to that and instantly view dielectric values on the viewer. And then Kyle had calibrations that he provided to us, which then we can now get density values from. And then I'll just point out that there's a number of other options that we can look at here, which is dielectric height, quality, speed of collection, the opposite of density air voids. So that's what we're seeing here on this screen.
And just one note for the group, if you look at that legend, it's the opposite of what a lot of you are used to with looking at the density, where in this case, the cooler colors are higher density and the warmer colors, the reddish and orangish.
Oh yeah, thanks for
greenish
pointing that
are
out.
lower.
And then, so
Yep.
this legend is fully customizable. I can add as many increments as I want. I guess part of the challenge is the color scale and making it make sense when you actually see it in the viewer. So thanks for pointing that out. So blue is good, red is bad. That's what we're looking at right now.
Mike, can I just to add on to that? So Kyle and all, why we inverted the scale this direction, because it was extremely confusing looking at the DPS data with respect to thermal data and intelligent compaction data when the color scales were inverted from each other. So it's a lot easier to be panning through temperatures for thermal profiling and intelligent compaction, and then also looking at the DPS when the color palettes match. And so that's why we inverted it, because otherwise you had it in your head. You had to keep flipping it as you're looking at each other of what was more of a concern versus less of a concern. So that's, oh wait, oh, you have it the opposite way.
Yeah, I guess I opened up a project.
The old, so Kyle, ignore everything I said. So we inverted it originally. We have it inverted. So the cooler colors, I should stop talking. I didn't realize you had an old legend in here, Mike. So we inverted it before because it was what Mike had here. But we inverted it to match thermal profiling. So the blues are supposed to be the lower dielectric, lower density values. So sorry for confusing things. I thought you were using the latest one that we're using for the class, Mike. Sorry.
Well, Rebecca, you're in good shape because that now we know beyond a reasonable doubt that in this case, cooler colors are lower moving forward, because that's also what the vendors use with their technology. So
yep, good. Yep.
It was worth spending time on that because
here we go.
Yeah.
All right. Well, thanks for pointing that out, because I guess it will be a little bit of a, you'll have to use your imagination just a tiny bit more here to make this all make sense. But again, the nice thing about having this standardized platform is we have multiple technologies in here. And what I can do is I can do a split screen with the DPS data up top and then just the paver mount thermal profiling data here at the bottom. And what I can do is I can zoom in here. And sorry, just as we were talking, blue up top here is good density. Blue on bottom is low temperatures. So a little bit opposite. So I think the differences will prove the point, maybe not the colors. So, but right here I can pan, I can see both sets of data. I can move to the other paver stop area, which is right here, and I can see a corresponding drop in density from the DPS data. I can right click search this data. I could see when it was scanned with the DPS. which sensor it was, lat long, the speed it was collected, dielectric value, height, quality, and then based off of the calibration that Kyle provides, the density and the air voids. So same information, I can right click down here in the paper mount thermal profiling data. And it's going to take just an extra second here. But so at the paver stop, we were getting material out right out the back of the paver that was about 185-ish degrees. So a lot cooler than we'd like. So so there's this example. There's also, try not to touch all my Zoom stuff in the way. So I could see one lane, I could see both lanes. I'm going to turn on both lanes really quick. This was going. So these projects do, I think this is 500 and change megabytes. So it does take just a second to refresh some of these maps here. We get other much larger projects. This one's trimmed down with just a couple days of data on each technology. So now we could see the other lane. Not all of the lane had DPS data collected on it. I just wanted to bring you over to, oh, actually I'm going to scroll over to the right. I have one more thing I got to point out here, and then I think I got to move to analysis here before I run out of time. So again, down here on the thermal data, what we have is there's this cooler strip of data on the edge. And then up here on the DPS data, you can see the corresponding lower DPS values. So again, there's some good correlations here. These were just a couple examples that I had ready to go this time. These are all the different data types that we can view based on the technology. So again, I went over the list for dielectric profiler system, but for the thermal profiling, we got speed and temperature. And then for the compactor, we got pass count, speed, temperature change, stiffness, frequency, amplitude, impacts per foot. So we could see all these different data types, and right here in the Veda software and do our comparison. So I'm going to switch to analysis here and show that to you before we stop. And I think I have this preloaded here. One of the suggestions we had was just the a percent within limits, and I just put in a, oh, sorry, I'm going to do density. I just threw in a quick, minimum density of 92%, and of the lot or sublot, we want 90% of all the data to achieve that. So I can go ahead and now run the analysis. And this goes fairly quick because I'm just analyzing the DPS data itself. So in Veda, we organize this data into what we call lots, and a lot is a lane, a lift, and a material that was paved the same day, which is more or less the information you can see in the title of the lot. So this software, as I was talking about, will get some analysis results. So we have I'm going to go to dielectric because that's a little better distribution here, but we get a chart, we get some univariate statistics up here at the top. So for this first lot, our dielectric values, the mean dielectric value is 5.46. You get your standard deviation, min and max. We can, again, because we have a calibration, I can see that same information as density. So the mean density was 94.9. This software can also slice and dice these entire lots into what we call sublots. I had the settings at 150 feet, which matches our paper mount thermal profiling. So I can go here and now I can view oh, there's no DPS data for that first little bit. But I could view this DPS data here. So this red rectangle here indicates the sublot that I'm looking at based on the chart that I have. And we have, this is the percent within limits that this one passed. It was 99.8% of the dielectric data was over the 92% threshold. So, and then again, the statistics on min, max, mean of the densities. And then we can get a chart of the acceptance. Again, this first 8,000 feet, there is no DPS data to make the comparison. But over here, there is DPS data, and it was all of these 150-foot sublots were past our test here. So some of these other lots are not so much. So I can see that, you know, we have a number of, each bar is 150 feet. So there's a number of sublots that just didn't have the 92%. So I can see that same information here in the table and scroll down. So this was 78. Only 78% was above 92, had a density of 92 or higher. So sorry, I keep lots of percentages here, but you can kind of see just on the viewer, there's more variability in the temperatures, or sorry, not temperatures, the densities based on the legend here on the right. So I think I just went over here a minute or two. So Kyle, was there anything else specifically you want me to show the group, or any questions before we move on?
No, that was perfect. Thank you very much, Mike. So, and I think we're doing all right on time. We have 15 minutes for discussion / break now.
Okay.
So, yeah, I think the main points that I hope that Mike and I were able to get across is that, you know, one, initially I wanted to show that just the on-site technology with the tools that are available with the manufacturer software are extremely useful and can be helpful when you're out there testing with this technology if the user is properly trained. But then furthermore, I think Mike did a great job of showing, you know, how many different things lead to either getting really good consistent density or not. And we have a lot of tools out there. MnDOT is blessed to be able to have a lot of intelligent construction technologies out there on our projects to see exactly what's going on from a process control. But generally speaking, what we're using at the end of the day for our density assessment is a couple holes every, you know, few hundred tons or so of pavement. And that's where I think, you know, with some of this a little bit more advanced analysis, it becomes clear, even something as simple as the vibratory roller missing spots periodically. With the way we're currently doing our density analysis, most of the cores probably didn't catch that. And I don't know how long that was going on before it was corrected, but figuring out a way to get these full coverage density maps incorporated in our process can have huge dividends. And so I'm thankful to Mike and Rebecca's group for providing all that different intelligent construction technology information. And I think it's a good challenge for this group to see how far we can take this to improving the way we do our process, because these are correctable things and it's not easy. It's a really complicated thing to get everything, all your ducks in a row, and to build a consistent, well compacted pavement. But I think as an agency, we can provide the incentive monetarily and otherwise for contractors to get that done, because it's worth a lot in terms of the product we're going to get and the density we're going to get in the field. So it's not too hard to look at these plots and envision, a not so far future where the roller compactors and the paver mounted thermal profile is feeding information, and the DPS is feeding information into a automated loop that helps us get these things corrected, you know, with our process, you know, eventually in an automated way. So with that, I guess I wanted to let Mike have a chance to, or Rebecca if she's on, to answer the question about the GPS accuracy from Rob Hinman.
Where is my, that's in the chat, you say?
Yeah, he asked, Mike, did you use the same manufacturer and accuracy GPS antennas for ICPM, TP, and DPS? And I answered in the chat about the DPS, but.
Okay, yeah, thanks for doing that. So the, as I indicated before, we've been at full deployment for intelligent compaction and paver mount thermal profiling for roughly 4 years. And currently we require a, what we call a high accuracy correction. So all of this data should be accurate to within 2 inches for IC and thermal. So that's, I guess if that answers your question, and I didn't see, Kyle, your response, but I assume you're.
Yeah, the only other thing I mentioned is that I know at the DPS technology, the offset between where the receiver for the GPS and where the actual measurement was applied is accounted for in the manufacturer equipment, and I wasn't sure if that's the case with the PMTP and IC.
Yeah, so for intelligent compaction, there the contractor is required to use a rover and verify the edges of the drum itself.
Yeah.
For paver mount thermal profiling, there's, you know, depending on the vendor, it's a little easier to make those adjustments than, so certain, I guess my answer is certain vendors it's easier, other vendors it's not as easy. But I think we are getting the accuracy left, right. There are some vendors where the receiver compared to where the data scanned is shifted. So there might be some longitudinal differences in the data. If I scrolled over to those paver stops, I think you'd see that there might be, you could see the paver stop for thermal was at 2895, and then you could see it's almost an additional 10 feet shifted for the DPS. So there is a little bit of longitudinal difference for our thermal data, but we haven't, now that all these technologies are compared to each other, I guess we're starting to see a little bit more of those differences, but independently that isn't impacting our incentives, disincentives, and requirements for any individual technology.
Okay, thanks, Mike. So, and then the other question Rich Giesel had is, what is dielectric height? And that's just the height above the pavement that the sensors are. And the reason that's included is if you have a height that's out of tolerance in terms of how the distance between the sensor and the surface, that can affect our dielectric accuracy. So that's the reason we're tracking that. And I forgot to ask Rob, did Mike and I answer your question?
Yes.
Okay.
Yeah, did a great job.
Okay, and then Rich Giesel, how about your question? Does that make sense?
Yeah, yes, Kyle. I just I would have called it sensor height, I guess. I wasn't connecting dielectric and height as the height of the sensor. So
that's a good comment, and that's actually also a good segue to, I wanted to mention that, you know, we don't need to be rigid with our meeting format and all that. So if you have suggestions, questions, please feel comfortable making them. That's kind of the purpose of a technical working group, is to work together and make suggestions. So that's one thing we'll note. is maybe calling that sensor height, which I think would be a little bit clearer. Dielectric height could be maybe depth of penetration of the measurement and many other things. So thanks for that, Rich. Rich Hamilton said, is the assumption moving forward that RTK accuracy will be needed for DPS? That's kind of a loaded question. I think at Minnesota, our plans are to follow the requirements that we have for the other intelligent construction technologies to require RTK accuracy. But as you saw from some of the analysis that you can do on site, it's definitely a useful technology, even if you don't have RTK accuracy. So that's probably going to be a state-by-state determination on that. Unless Rebecca, do you have anything to add to that?
I was just typing in the chat box. Sorry, Kyle, I'll stop that. I think you hit it perfectly. So really, it just depends on the state and how they plan on deploying the different technologies. So if all you're deploying is DPS and you're not too worried about overlaying some of your cores and stuff, that gets a little tricky when you have low accuracy and then you have high accuracy for where your core locations are later on. And coming back and making sure the two different data types overlay within Beta. I'm not talking about the other calibrations and stuff that Kyle's gone through in the past out in the field, but more so in Beta, if you're trying to overlay different things on top of each other for technologies, it's easier to do so if they're all high accuracy. So if you're a state that you're going to be using intelligent compaction thermal profiling and you're importing test measurements into Beta as well, because those you would be using station and offset or a XY coordinate for, it's nice to have everything as high accuracy. Now, if you're just using one technology and that's the DPS and you don't plan on really trying to tie it to anything else and overlay it, then it's probably not as critical and stuff. So, but tying things together to make a virtual roadway, it does help with having high accuracy.
Yeah, and one thing just to piggyback on what Rebecca is saying, kind of an additional plug. I'm a big fan of doing what it takes to get high accuracy GPS associated with this technology. It can save you a little bit of a pain in terms of checking the accuracy of your DPS too, because I can tell you it's not easy to get dielectric measurements at all your random core locations with a spot check. You either got to do it late at night or really early in the morning, at least in Minnesota. So if you can get a high accuracy coordinates on your full coverage map and then also high accuracy coordinates on your cores, that might eliminate a very difficult logistical step to checking the accuracy of your DPS if you can just check your full coverage map versus the cores after the fact. And that's something we're looking into at Minnesota. So Rich Hamilton, does that answer your question?
Yes, thank you.
Okay. So Fabricio's done an outstanding job as part of the pooled fund. He's been tasked with both precision and bias testing, and then also equipment and operator certification type work. And so he's going to present for us here. And this fits in with our umbrella topic number 2 that Fabricio is our champion for.
All right, good morning, everyone. What I'll do is present to you some of the results that we obtained after conducting a couple of studies at pretty much at NCAT and that took place during the reconstruction cycle last year. And this involved task 2 and 3. 2 is related to development of equipment and operator certification procedure analysis methods. And the motivation for that one was related to the expectation of that new vendors with the similar technologies are gonna appear later on. They're gonna join the industry, and we need to have ways to evaluate what potential differences are going to be between the existing technologies and the new ones. And at the same time, for instance, if we plan to have dedicated sensors, dedicated antennas to be in the lab, and then you want to move that to the field. Is that antenna also going to perform similarly to the antennas that are in the field? Or simply you want to rotate those antennas and have some work in the lab or some go to the field. Either way, you want to make sure that all of them are working similarly and providing similar results. In terms of test 3, development of precision and bias statements, that's pretty much part of every standard practice that you may encounter. Either if you follow ASTM or AASHTO, you may want to know what are those statements, and when you're obtaining results and comparing results versus what's happening within the same lab, or if you want to compare with other labs, those are going to tell you if you're within a significant level of precision. So the first part is going to be dedicated to what we propose in terms of laboratory certification program that involves having operators and several equipment or several sensors evaluated and compared to see if they are showing similarities or if they are creating some bias when we are obtaining those or measuring the electric values in the lab. And for that, we use PUCs, compacted superpaired jet array compactor samples, and we evaluated these 3 different statistical assessments. The first one is concordance correlation coefficient. That's related to having values that are going to be close to the identity line. We use the total deviation index, which is comparing pairs of values. In this case, you can compare 2 different sensors, or you can compare operators, either way. And then you have to establish a limit. And then you also have coverage probability, which is similar. Those two, the total deviation index and the coverage probability, are pretty much the same. Basically, what we're seeing is what we're doing is seeing the results from a different perspective. One is going to be defining range, and the other one is looking at the probability to be within that range. But those 3 are the ones that we consider that we could use to evaluate agreement and concordance between lab and between sensors or operators. And I'm gonna show some of the results that we obtained. In order to do that, we prepared compacted samples using 2 different mixtures. One was a 9.5 millimeter mix, was a dense graded mix, and we also have a 19 millimeter coarse graded mix, just to have different mixtures that we can compare and have at least a wider spectrum of results. At the same time, we created compacted samples at 4 different levels, starting at 3%, 6%, 9%, and 12%. And for all of them, we obtain dielectric values following the standard protocol. And here, I'm just going to show what we did initially with 3 different sensors that we had available. And we wanted to compare those 2 mixes, and we also have another mix that we had available in the lab. That was our trial mix that basically we used to learn how to operate the equipment. We added that mix in there, and you can see that when we're comparing several of those sensors, well, those 3 sensors, for all the cases, we were able to meet all those parameters. We wanted to be, above 97.5% on the concordance correlation, below 0.06 in that TDI or index. And also we wanted to be above 90% or 0.90 on coverage probability. So that basically what is telling us is all this, when we compare 207 versus 206 or one sensor versus the other, when we have all those 3 mixes, all of them were showing, similarities in a statistically, way that we were able to prove that. We did actually found out later on that the 90 millimeter mix was a little bit tricky to deal with. And then we decided to split the results. So now here I'm showing more sensors that we had at that time. We had later on we had 6, and then we send those samples to MinDOT and Kyle's group. They were able to also test the same samples, and we added more. But here I'm showing 6 different sensors that we had, and we separated those 2 mixes. And we noticed that the 90mm mix was showing us slightly lower results, and that sort of makes sense. Made sense because we were observing a little bit more variability on the results with the 90mm. When we went and checked the total deviation index, here we found a couple of instances where we pretty much failed one, and the other one was right at the range that we were expecting, and that pretty much led us to do more investigation of what was happening with those mixes. And basically we found that the high level of airboids, the 12%, we had several samples that we had a lot of variability, and it was difficult to obtain repeatable results. And we observed that with all the different sensors, and you can see that in most cases the 19mm was showing higher values, which in this case we don't want to go above 0.06. And for the 9mm, every single pair pass that criteria. The coverage probability is going to show us the same results as before. In this case, it's mostly or more easy to identify that this pair we also had an issue. And again, we went back. It was the 90mm. We identified a couple of samples that were behaving differently, or not the samples. It was just that we couldn't have repeatable values, and we were thinking maybe it's the texture of the mix, something that may have happened, or how the airboards were interconnected within that mix. Different ideas that we had, but we did notice that of 12% with the 19mm mix, it was showing us this erratic behavior, and we believe that may be a limitation in terms of establishing what is the maximum level that we want to evaluate in the lab. And here what I'm showing is that we also perform some outlier analysis. We have here, we noticed that there's a little bit more scattered results when comparing a couple of sensors in the 19mm mix. And then when we went and evaluated, having an average of both sensors versus the difference, and establishing a range of that we can establish as the limit to identify the outliers. So we found that that's what was happening at the lowest dielectric values, that of course are also the high airboard samples. And we were able to identify that that was the same behavior every single time with a couple of samples. And we were failing a couple of those criteria. And after removing those outliers, considering that there was something going on with that, we cannot simply eliminate data points. We had to justify those, and we decided, well, yeah, that is something that we can do. And after eliminating some of those outliers, we were able to get back or at least pass those different criteria. For this, we developed a web application where you can pretty much create a CSV file, identifying one instrument versus the other, one sensor versus another. You can add several mixes, and then it's gonna plot you the identity line. It's gonna compute all those 3 different criteria, and you can compare with the established threshold, and it's gonna tell you if it's passing or is failing at the end. And here's also gonna show you what is that outlier analysis or outlier procedure that we developed. And you can see if there are some of those data points that may be considered outliers. Just you need to do further evaluation. And for the moment, it is located in a web page or a web application. You can just you follow the link, and it's gonna pretty much allow you to upload that CSV file, and it's gonna tell you all these different results. And with that, we are recommending this methodology. Basically, compact the 3 gyratory samples at a minimum of 3 airborne levels between 3 and 10%. So we're pretty much recommending what we did before without the 12% airborne level. We recommended to use or follow AASHTO T331, which is the core log methodology. One operator must test all the samples using at least 2 sensors. And at the end, using that application, calculate all those different statistical parameters. And also conduct some outlier analysis, investigate the source, and adjust the analysis accordingly. And if those 3 items meet the respective criteria, then we can say that the operator and equipment can be certified. Okay, so that's basically what we have in terms of laboratory. We can also use this methodology to evaluate if there's going to be some bias, and the same samples were sent out to FHWA, or the Turnpike. No, I'm sorry, it was the lab. I'm sorry, I forgot.
Turner Fairbank.
That one. Thank you very much. And they were able to evaluate the same samples with their own sensors, and they were able to identify, as you can see here, there's some bias between sensor 194 and 211, and that's what's repeated with other sensors. So 194 was showing exactly this behavior, so a slight deviation from the quality. And at the end, when you plot the same or use the same methodology we've established to obtain or measure potential outliers, you can see that everything tends to go to one side. And what we would like to see is something scattered around the 0 value. So that was another way to utilize the recommended methodology. All right, next we have this proposed field certification program, which basically follows exactly or closely to what was done with AASHTO R56 for inertial profilers, basically to establish accuracy and repeatability, between sensors or among sensors. In this case, we didn't have a large database similar to what was done in AASHTO R56. So we had to generate artificial profiles. So we generated reference profiles, and we generated candidate profiles. And following something similar to AASHTO R56. In this case, we also decided to utilize a simple score system using the root mean square percent error, and which is easy to identify. It's just, we're looking for a percent or a score, similar to what is done in R56. And here's, basically, we're using the root mean square percent error. If we subtract from 100, you can obtain a score. And as I said before, we created artificial profiles, basically following a 400-foot section. We created a reference profile, and then we started to add variability, by a standard deviation, so plus or minus, and created, different scores based on that. If it was a score of 100, we were pretty much matching the reference and the candidate profiles. And there's some deviation, you'll have to start to see a lower score. And in order to do that, we basically use ME modeling, to establish what is the effect on performance when you have differences in those profiles. We use 4 different locations around the country with in a simulated a test payment section. And basically what we did is use AASHTOware to evaluate reference profiles, added deviation or variability to those profiles, and then created also candidate profiles and see how can those scores vary when we add variability in both the reference and the candidate profiles. So basically we generated randomly readings of airboids. We had 9 reference profiles at 3 different levels, 4, 7, and 10%. And for each of those, we have around 540 candidates profiles per reference. And we had the end scores between reference and each candidate profiles. And here's basically what we end up at the end. We considered all the different distresses and how having all those different differences in airboids were going to affect performance. And at the end, we come up with this this scoring system, which basically, for accuracy, when we're evaluating a new device, or we want to, provide a certification for a device and an operator in the field, we're recommended that for accuracy, there has to be an agreement of about 92%. Basically, that's the score that we are asking, similar to what we do with inertial profilers. So in that case, that will be less than 10% and 10% error in predictive performance in at least 95% of the comparisons. And for repeatability, an agreement of 94, or a score minimum of 94, and that will provide us 5% less error or less. And we also created an application, this in case in Excel. You can see that it's going to provide you with the steps. It's relatively easy to utilize. You need to create CSV files, upload those into the Excel application, and then you can calculate both accuracy and repeatability, or you can do each individually. But you will see is the plots of reference profile versus 10 candidate profiles. And what it's going to do is it's going to show you a score comparing every single candidate profile versus reference. That will be for accuracy, and a repeatability results or scores comparing among candidate profiles. And at the end, you will have something like this. So these individual scores are pretty much each candidate profile compared to the reference profile. And then this is not showing all of them, but it's basically comparing among all the different candidate profiles. And if we meet those minimum scores, we're going to be able to certify the different sensors and operators in the field. Again, so
Fabricio, we have a question in the chat that I figure you want to address now.
Sure.
Rich Hamilton says, how is the reference profile obtained?
That was artificially generated. Basically, going back to here, this one is, for example, we basically established 3 different levels of airboids, 7, 4, and 12%. I'm sorry, 10%, and generated artificially profile and for each of those density levels. So basically, randomly we generated this profile, and then we did that for 4%, one for 10%, and then for each one we created candidate profiles, adding standard deviation, up and down, or plus or minus. In this case, you can see here is the case that we had minus, but the idea was to add some differences between the reference and the candidate profiles, and evaluate what was the effect in performance, and to compute the score that is based on simulated performance.
And then Fabricio, while we got you taking a break from the presentation, the other question I actually had was kind of for the group, but mostly for you, to get the tools that you're presenting available for use by the DPS pooled fund. I can't remember, did we decide we're going to have them posted on our website with a short tutorial?
I think, yeah, I think that was the case.
Okay.
Yeah.
And then the final report for Fabricio's work, just a note here that has some of the context too, for the questions of where the different reference profiles come from and all that, and the different statistical measures is also posted on the website under our publications tab. So go ahead, Fabricio.
All right, so
Fabricio,
Yes,
just clarification. So the reference profile is already built in your software, right? So the user do not necessarily need to get their own reference profile.
Well,
Right.
the reference profile is going to be similar to what you have for inertial profilers. You're going to need a third-party device. In this case, what we used at the track was a nuclear gauge that we obtain, you know, a reading every food, and then that all later on we correlated directly with several cores. You know, we're talking about, you know, more than 10 cores, and we were confident that that was sort of a good exercise to start with to obtain a reference profile. So this is going to have to be implemented similar to H2R56. You know, we're probably going to have certification centers that are going to have a known profile that they can use to verify it, or this can be done later on during you know, construction that is of a high profile project, like it's going to happen in Main Road. You know, this exercise is going to be repeated by Kyle, and he's going to test two different devices and see, you know, how they compare in terms of these scores.
Yep, and then just to add a little context to that, we're planning on we're going to be doing it on a shoulder at Min Road where we've been given clearance to take more frequent cores too. So in this case, our reference profile will be based on the cores themselves, because as many of you know, there's uncertainty with the nuclear device as well. So the goal with that kind of piggyback experiment was to take the advice from Fabricio and then try to supplement it with a core with a additional core based reference profile.
Mm-hmm. Yeah, I also noticed another question. Let me see, from Rich. Did the NCAT data indicated that sensors that vary in the electric reading could be aligned by application of a factor? What we didn't obtain any bias. The one that I presented before was comparing other sensors that in the lab, but we didn't observe any bias or differences in repeatability following this process in our study. And that's something that has to be discussed within the group to see if it's going to be convenient to apply any factor if a bias was to be discovered. So that's something I think is to continue with the group and discussions with the industry and agencies, I think. So basically the recommendation is to select at least 200 foot pavement sections that have either known you know, density levels or differences in mix types, you know, coarse versus fine, or different nominal sizes. Then we want to obtain 10 profiles. Those are going to be the candidate profiles along that 100 foot mark line on that section. So you can pretty much follow, or you know, every candidate profile has to follow the same line. And then we can obtain a reference profile, as I said, having another device that can be, you know, correlated with cores, you know, in a more practical way. See? And then basically generate CSV files for the reference, and another file for the candidate profiles, and use the Excel tool to compute accuracy and repeatability scores. In the case of inertial profilers, you do that with Profile, the software that was generated by the same, I think it's the same group from Beta, but it's the same sort of the same idea, having those candidate reference profiles evaluated in a application that can allow you to compute accuracy and repeatability scores, and from that establish if the certification applies for field testing. Next is briefly, I'm going to go through precision and bias statements that we developed at NCAT. And at that time, we had 9 sensors. We basically follow ASTM A691. And here I'm showing one of the checks that we need to conduct with the H and K consistency statistics. In this case, pretty much we were able to meet all those. In some instances, we were close to marginal, but following the practice, we were fine. And these are for POCs evaluated in the lab. We also need to check average values versus standard deviations that are basically the step prior to obtaining the statements. And in the table, you can see, well, we reported the average statement for within the lab and the average for the between lab. The maximum is going to give you what is the statement. So we are looking for, differences of 0.11 or within the lab, or 0.12, 0.25 of the dielectric. These are the values reported directly from POCs, and this is what you would expect to see if you are measuring this within the same lab, or if you want to compare 2 different labs. This is the maximum differences that you may expect between labs. Now we decided to see what I know by estimating density from all those different results that we had before, what will be the equivalent in terms of density. So we were able to compare those to ASTM D2726 or 6754, which is the bulk specific gravity test, and the other one is the vacuum or core lock. And you compare the maximum in terms of within the lab is 1.67, and that's significantly below the single operator or the within the lab for those 2. So we're obtaining better results when we are using these in terms of density. And when we compare that results or those results between lab with the same ones for these 2 different methods, we are again slightly below, which is good in terms of how the technology is able to measure density in the lab, or at least estimate density in the lab. Now in terms of field statements, we have 6 sensors. That's the minimum that we can utilize to obtain the statements. And in the case, we use 8 sections at the test track that were built last year. We also evaluated, measure at the joint, and we measure within each of the sections. And we also follow ASTM E6191, and we check H and K consistency statistics. We wanted to evaluate or compare what if there was going to be any joint effects in terms of the statements, because if that was the case, we will have to generate individual statements or dedicated statements when we were to measure density at the joints. Here in some cases, we were able to observe that the joint, when we were measuring the electric values at the joint, were slightly below compared to other locations within the section. But in other cases, we didn't observe differences. So we wanted to evaluate even more to see if it was a need to separate field statements with respect to the joint versus the rest of the section. Here I'm showing again H statistics. We want that to be within those 2 range values that come directly from ASTM E691. Also the K consistency statistics. And here I'm showing standard deviation for the within the lab parameter. And I wanted to show here because in some cases, when we have this section with the J is the joint, I forgot to mention that before. In some cases, we observed that was showing higher variability with respect to of the other location within the section. In other cases, it was very similar. In other cases, it was the opposite. So after conducting analysis, statistical analysis, we discovered that there's no difference in terms of the statements when we talk about measuring the electrics at the joint or at other location within the section, which is good in my opinion, because we don't need to establish a dedicated statement for the joint. And it is also a confirmation that the device is not affected by any variability at the joint. Is simply reporting the dielectric, and it should not be affected by having that different location within the pavement. Again, wanted to check average versus standard deviations. Everything looked fine. I'm showing here what are the statements then in terms of field statements, slightly higher compared to the lab. That was expected. And when we transform those to density and compare those to the nuclear gauge and the electromagnetic surface contact gauges, we also obtain lower statements compared to those two different devices. And again, showing that we are obtaining better results when we estimate density from DPS technology. And what is the recommended methodology in this case? Well, is select at least 6 different sensors, which is the minimum established by ASTM. We would like to have or perform equipment consistency verification on each sensor, following the testing protocol. We recommended to have 100 feet of any pavement section to be tested. We added a metal plate to establish what is the beginning at the end, but any means available to clearly define what is the beginning at the end of the section, it is valid. Sometimes GPS is not that accurate, but when you add a metal plate, you have full reflection, and then it is easy to identify that peak value when you start and when you finish the section. And then those two are going to be always the same beginning and ending point of the profile. Basically place the one sensor 6 inches from the longitudinal joint, and then at least place another sensor. You can have more sensors if you are capable along the transverse bar if you're using GSSI technology, and repeat at least or obtain 3 replicates for each location, joint or anyone else within the section, and then follow ASTM E691 to determine adequacy of the data and determine statements. And also, we can also continue, evaluating for outliers or the other ways to identify any potential effects, either the joint or other potential locations. We also evaluated the age of the pavement, and we had several sections that we also had, values or profiles measured near the age, and that was no a significant effect or differences in comparing to other locations within the pavement section. And with that, pretty much wanted to thank you, and I hope to continue, providing more information and working with this exciting to me, technology in the future in terms of density readings and performance. Thanks.
Well, thank you very much, Fabricio. A lot of really useful information there. You've already answered some questions in the chat, I think. Is there any questions that the group wants to ask Fabricio about his work?
Fabricio, would you mind going back, sharing your screen again, going back to the multi-lab precision?
Yes, sir. Just one second.
Thank you.
For the field or the?
For the field, yes.
Okay. There you go.
Great.
Oh, I'm sorry. Yes, we're back.
Very impressive results there. Thank you.
Yes, and again, what Kyle and his group is doing in MinRoad is to continue this process and verifying that what we have found in this study, and again that can be done not only at this type of projects. It can be confirmed later on on other projects when you are able to compare or have replicate results.
Yeah, and I don't know if the only thing I heard on my end when we got to this slide from you, Rob, was impressive results. Did you say anything before that?
No, I was looking at the different AASHTO test methods for cores and core lock and for calculating density, and I was just trying to get a flavor for where things were at from the field versus lab setting there too. And so I mean it's impressive results.
And one thing I think that we'll do with our testing in August at MinRoad, in addition to the creating those reference profiles and repeating Fabricio's measurements there, is we'll also be doing precision and bias testing following Fabricio's protocols. And we've actually already done that on existing pavement. And I'll be interested to see if we can get on the pavement as quickly as possible after it's paved to see what the difference in precision is right after construction versus waiting a few days. Because my understanding, Fabricio, this pavement was recently paved, but it wasn't like right behind the final roller when you did this testing. Is that correct?
Well, yeah, we had to wait a couple hours at least.
Oh, okay, so it was same day though.
Yes. Yeah.
Okay, good. Yeah, so it'll be interesting also to see the effect of that. And then I guess one question for the group, is there anything, since we have the opportunity to try to replicate this experiment at MinRoad, that you'd like to see us incorporate with our testing that comes to mind?
Kyle, I did some 24-hour difference comparisons with cores and dielectric, and at 24 hours after the mat had cooled, I got less deviation and better results than I did with the fresh mat, mostly because the pavement was cool and had set well enough that you could take a core without damaging it or deforming the mix. So that's something else you might look at.
Interesting. Yeah, because we always think about how the environment and equipment is going to affect our precision of the dielectric measurement, and then just treat the cores as ground truth, whatever we get from the cores. But that's another thing to take into account, is
the cores get more consistent after one day.
Yeah.
Less damage to them, so they correlate, the readings correlate better.
Interesting. Thanks, Rich.
So Fabricio, so this means each state needs to establish their own reference sensor measurements profile, right?
No, it's gonna depend on whether you want or to have that field certification in place. It's like with the inertial profilers. I think in the country we only have 4 or 5 centers, taking care of that.
Yeah, that's why I'm trying to think about the profiler system.
And
so they maybe establish similar centers around the country to certify.
Yeah, and all that it's gonna become more of a need. You start seeing more and more different vendors trying to enter the market.
Yeah.
With profilers, the initial profilers, you now have more than 10 or even more vendors in technologies available, and even other different technologies trying to simulate inertial profilers, and some have been able to pass the certification process, even though they are not profilers per se. But that's something that may need to be considered later on. And as long as we continue to see more and more different devices, I think you want to have some way to have a sense of how they vary, and have some way to evaluate them to see if they're gonna be able to perform similarly, especially if an agency may have one device from vendor X, and they're gonna be consultants or contractors having other technologies, and you may want to at least have an idea how different they are. And the same with inertial profilers. As long as they pass or obtain the certification, they are considered to be good to go and use in a project.
I guess I have one comment and then a question. I believe at Minnesota, the baseline or the profile that's used for comparison is generated by a golden profiler, not necessarily an independent measure like what you used with the Newt gauge, or what we would be using if we did cores. So my follow-up question is, do you think that type of a procedure could be used for DPS, where you have a golden DPS that, for example, the agency might put out there and say, this is the profile, and not necessarily just look at magnitude of the response, but just the variation in the response if you have different vendors with different frequency contents and whatnot. Would we be able to do a similar thing where we have a golden DPS that the agency puts out on the test site, and then you pass or fail technologies based on that?
Yeah, and I think based also on the statements that we obtain, which are indicating that the DPS technology is better than nuclear gauges or others. Yeah, that basically we were not using the ideal goal or whatever reference. But yeah, I think if we may have something as you're describing, that will be even better, because we already know that we are obtaining more accurate and precise results with DPS versus other known technologies that are out there.
And then I see John said we use SurPro for the reference profile for our high speeds. Do you want to expand on that at all, John?
That's just what you were referring to with your golden piece of technology. It's just a little bit more accurate, and then we compare all our high speeds to that generated profile for candidate profiles.
Yeah, that's the same we had at NCAT. Yeah.
Thanks, John. All right, so we are at the 11:15 part of the agenda here. So I'm basically, Steve Cooper thought it might be a good idea for me to update on the presentation I gave at the previous technical working group meeting. So I'm going to take kind of a brief overview on some of the items that we identified as challenges in the first technical working group meeting and then hand it over to Robert before he gives an update on his spreadsheet that he presented at the initial technical working group meeting, and then we'll discuss and wrap up after that. So I'll now pull up my presentation. Can you guys see my
Yes,
slide?
we can.
Okay, so this presentation actually I gave with Dennis at the previous technical working group meeting, but he wasn't able to make this meeting today, so I'll be giving it without him. But the basic point is that when we're looking at using DPS as an acceptance method, we're looking at doing it in various different ways that all have their unique challenges and potential solutions. So, you know, one solution might be similar to what Rich is looking at in Alaska, which the agency is using the DPS for the testing. One might be more similar to what Minnesota or Ohio might be looking at, which is contractor DPS verified by an agency DPS, and then of course verified by cores too. So we're going to look at a few of the challenges associated with all these different techniques, and then just give a little bit of an update on what we've been doing to try to address some of them. So and one thing just that I always note on this presentation when you talk about challenges is just remembering the potential and the goal, which is a much needed improvement in how we do our assessments of HMA density. And these are challenges that, in my opinion, are worth putting our time and effort and resources towards addressing. So with the QA program, this is something that Dennis would normally talk about, but there's these various kind of aspects of a general QA program, and we've touched on some of these actually with Fabricio's presentation here, and I think you guys are well aware of these, so I'm not going to harp on this slide too long. But one of the challenges that you saw listed before was making sure you're just using equipment that is precise and unbiased. That's the kind of the basis of being able to be successful with your quality assurance. And we came up with earlier a specification for dielectric profiling systems that basically if you met these performance measures, you knew you were using a piece of equipment that you could bring out into the field and get good results when measuring dielectric behind the final roller compactor. One thing that we're in the process of working on is doing something similar with the laboratory component, which is basically taking the production mix and locking in our dielectric to density conversion using these gyratory compacted asphalt mixture specimens. So there's been a couple iterations back and forth in terms of sending the specification and then getting comments back from Kurt and his committee. But basically we took what was written a bit too much like a research report or even a publication and tried to simplify it as much as possible to make it more of just a typical AASHTO spec where we're specifying the procedure and then these measures that I'm giving here in the table that are basically based on Fabricio's work on tasks 2 and 3 as part of our pooled fund, where we have these different measures that make sure the equipment is good. And these would be the type of measures that the manufacturers would be in charge of making sure that their equipment is hitting these necessary limits of statistical measures to make sure the technology is accurate and unbiased and precise in measuring dielectric of gyratory compacted specimens, and then also measures that us as users can use on each specimen to make sure that they're actually functioning correctly. And these on table 3 here of the current draft AASHTO spec are designed to be able to be completed quickly on each specimen. So the specimen dielectric variation is just the maximum difference between 3 orientations of the puck when you're measuring it with the device, and then making sure you're within the dielectric range of your HDPE puck that you're measuring with this technology. And like I said, we have a draft specification for that is going through, like I said, various iterations, but we hope to have that draft specification published as hopefully as soon as this year or maybe next. So the next topic is the sensor consistency throughout the day, and then also from day to day for the same sensor. And what we've been doing up to this year has been basically using swerve or repeat line tests to make sure our sensors are consistent relative to one another. And what we had listed last time at the beginning of this year was a possible future material that's closer to the AC range that we could use for our consistency check, and also a standardization. The HDPE that we initially started to evaluate was just too low of a dielectric compared to our asphalt, which is up around 5, 6, 7, as compared to the HDPE, which is down around 2.3 to 2.35. So just an update there. We've been testing this year with this new fiberglass material and seen really good results so far. And what I mean by really good results is we have a standard value that we know this technology, or that this piece of material should have in terms of dielectric result. And so not only can we compare between our 3 different sensors how close they are to one another versus this standard value, now we can actually test the same sensor over time. And we're really excited about that in terms of, one thing we want to do is make sure we're as standardized as possible when we go out there with this technology, so that any sort of variations due to temperature internally of the sensors, or ambient temperature, or basically anything that can cause changes in the sensors, which could also be how they're calibrated. If they're calibrated properly with the metal plate or the air calibration, we should be able to evaluate that with this standard block. And that's what we've been doing, and then testing it versus the repeat line test and swerve test that we have been doing in the past successfully as a means of evaluating this new method. And it's really good news, like I said, so far, in the sense that on the left you have the dielectric measured of the fiberglass, and then the right you have the dielectric of the asphalt from the repeat line tests. And this is just an example of all the different sensors on the left, middle, and right, which had slight discrepancies based on the height of the sensors. But the good news is even those slight discrepancies, as little as 0.02 here, showed up similarly with both the fiberglass and the repeat line with the AC. So that gives us the confidence with this standardized material that it is in fact reflecting how the sensors are performing with what we care about, which is our measurements of the asphalt itself. So we've done a lot of controlled tests with sensors in the different positions on our 2 different carts. And then, even an example where sensor 171 was measuring differently between the left and right carts, the repeatability with them in the same position showed almost exact with the fiberglass to what we saw in the change of our AC in terms of a magnitude of the dielectric. So that's an encouraging trend. One thing that we gave feedback on is that this is a pretty heavy specimen. So now we have a new specimen we got last week that has handles, and it's basically circular, so it's exactly the dimensions without having edge effects to make it easier on the user to be able to bring it out in the field. And the reason that's important is that we had specified doing these consistency checks throughout the day and have seen enough consistency with our sensors that we're just specifying it at the beginning and the end of the day now. But you want something, if you're going to have a standard material for this type of stuff, that you can bring out with you to the field each day, just to make sure your sensors are measuring consistent to themselves, and then also over time. And then this is just making sure we're running through our new fiberglass with the new ramps through the same protocol and comparing it to the old ramp and old fiberglass for consistency purposes. So that's something that we'll have a more detailed report on later. So this is basically what we've been doing in the field, is going out with our custom material, checking that our sensors are good relative to each other and the standard reference. And now we're standardized to our known dielectric value each day when we go out there to test on the project. And then of course we still do our swerve and repeat lines that we can make sure, okay, if the left sensor is measuring a little bit low and needs to be increased relative to the rest, or the right sensor is measuring high and needs to be decreased relative to the rest, for the standardization, it's showing up both in our swerve and our custom material to make sure those are consistent. The next thing we talked about is the need to monitor for changes in mix, because as we all know, different aggregates have different dielectric properties. And our solution for this, presented last time, is to use these gyratory pucks to be able to measure those without cutting any holes in the pavement, to get our calibration from dielectric to density, or presented as air voids in this slide. So the one thing I wanted to mention there is, and we kind of talked about it earlier, is how we actually check the accuracy of our conversion. And we've been doing spot checks at the core locations prior to them being cut, and we're looking into the possibility of just doing our routine full coverage assessment and then comparing it to the cores after the fact, which would require a high accuracy GPS for both the core locations and the DPS measurements. And that's what's presented here on this slide. And one thing I wanted to mention here is that UNH has been working on a statistical acceptance criteria for comparing our cores to our conversion using the gyratory samples. So the next question is, first of all, how do we eliminate this from happening, where we see a bias in what we're measuring out in the field in terms of our cores versus our predictions from the gyratory specimens? And the good news is we don't often see this type of a result, but it does still show up periodically. And that's one thing that we're hopeful we're addressing with this standardized material, to make sure if we are measuring lower, that'll be taken care of by standardizing to that fiberglass specimen. But we do need to have a procedure in place for what to do if something like this happens and we were deploying this technology. And again, UNH is looking at the process to make recommendations there. The routine data collection, I guess the one thing I wanted to touch on before giving the floor to Rob is that the simple push cart, it's doable, but from a deployable standpoint, that we've gotten feedback from the contractor that that we may need to have some advancements there, and that's one thing that we're looking at, that we demonstrated at our training event this past spring, is looking into whether it's robotics or other ways of getting our full coverage lines of data, or even doing a segue type procedure to push the cart, getting those 9 lines of continuous data across the lane is something that's a critical aspect in being able to deploy this technology is how exactly that gets done. And then, of course, our ability as an agency to check, do routine checks on contractor collected data to make sure that the data that's being collected is in fact following our protocols and unbiased and correct. So with that, I think I'll stop sharing my screen and give the floor to Rob to give us an update on his spreadsheet.
All right, well, hopefully the screen sharing works, and
It looks like it's coming up.
should see a little bit of a trying to enlarge the other screen on my side so I can have a little bit better image of what's going on. So really this is a summary of much of what's already said, but it's helpful in knowing how far we've actually come in a pretty short amount of time. It's my non-accurate, non-precise Venn diagram of how all these interact and so that we can implement the DPS technology on for not just quality control use, but quality acceptance and assurance. So as Kyle said, I apologize. My slides are a summary of the comments from the previous peer exchange. So they're pretty text heavy, and the good news is I'm not gonna read them all, right? I'm just gonna try to touch upon the highlights or the most important parts of them. There's a lot there, and the intent was for it to be a resource and for future use. So one of the primary concerns that was brought up numerous times was safety concerns, and particularly there's the combination of length of lane closures, collecting centerline data, night paving, long exhausting days, and it creates for a higher risk environment. And as Kyle mentioned, there's some potential solutions there, whether it be the autonomous or robotic data collection, vehicle mounted segways. I put a note down here that it's important to be aware of the max equipment collection speeds to collect valid data that and so we'll need to be cognizant of that. Oftentimes additional personnel are needed to assist, whether it's to give them breaks or take notes and coordinate the work. Coordination and communication are really going to be key along any of these different areas, and because we're going to have certainly very technical users and say less technical users for it, in both operating and doing and potentially even doing some of the analysis, and so related to the safety or the construction's concerns. Again, safety was highlighted repeatedly as a #1 concern, as well as limited resources. Whether those resources, I apologize, one moment. And have to do with equipment, personnel, costs. There's contractors a little bit leery of buying all this equipment, and then I apologize. I bought a young one underneath. So there's trade-offs that are likely going to have to happen for the contractor. And again, I apologize, lost my train of thought. So we go back. So there's going to be, we know there's going to be a learning curve to all this, and the videos that MnDOT has put together are going to help with some of that. There's also concerns about length and timing of collection, same day, next day, as we already heard. Contract language, working out some of the what ifs, such as rain events, and just even turnaround times for report analysis, and as Art previously discussed, the sensor consistency. We've discussed a lot of these, and I'm going to throw out some extras that were not directly discussed. So one of the concerns I at least expressed repeatedly, both on contractors and DOT side, were the cost, right? The cost relative to a paving project is relatively insignificant, but relative to just equipment purchases is a bit on the heavier side. And so one of the ways that could be helped address that is putting it in a project as part of a project requirement, whether it's a shadow project or pilot project, and certainly that line item would pass on to the state, and which potentially could be passed on to federal highway, right? So because there are that increased pavement service life benefits to offset those present costs. So nothing shady there, just realize that there are some opportunities to have less risk associated with that cost, and also then potentially having different line items for that work, whether it's related to a percentage of collection, one maybe for the equipment, another one for the percentages collection. So that way, again, reduces the contractor risk in implementation. There's also needs to be a good discussion about the incentives, and we offer bonuses for density. Typically, a lot of state DOTs offer bonuses off of density, and we may want to think about how to structure that for the improved performance that we'll get by seeing this real-time data, the DPS data. We talked about learning curves. So again, coordination is going to be really key for setting up the lane closures and timing of collection and coring, and documenting areas of interest, what's going on, right? So that's really helpful when you have the other intelligent technology, construction technologies, where you're able to overlay the thermal and the pass count, or whether they had the vibratory on or not, to see what's going on and to make those corrections real time. Kyle spoke recently just about the sensor consistency. So most of this has already been addressed in previous slides, so I'm not going to spend any time on here, but when I refer to these specs with the AASHTO, it's really in terms of national specifications rather than those that the state DOT would use, related to equipment and operator, and rather than all the how-to. So as mentioned, kind of developing a gold standard calibration block, where it looks like we're getting there, and so that's exciting to see. We're moving forward with operator and equipment certification, structuring the certification programs, working through, how many cores do you need to get accurate correlations and predictions. What's going to trigger more or less cores based on those results. There's certainly the big ever-present what to do with after a rain event or moisture in the morning, right? And so we'll need to do a little bit more work there to determine exactly how long we need to wait, hold off on data collection if there is a weather event. You know, is surface dry sufficient? And so there'll be a little bit of focus, hopefully at some point along those lines. We talked about puck height and sensitivity there. So I'll move through that. Some of the potential solutions, since there's going to be a different formatting, that's use the standard AASHTO MP39 file format for the intelligent construction data. Have as looks like Kyle's found out, and the pool fund group found out that the consistency checks are needed less frequently as they've gained experience, and it seems like right here with the that fiberglass that's very promising. Touched upon let's see, so I'm going to jump over to some of the state agency considerations. So Kyle also touched upon, right, we need to be compliant with federal regulations, right? So if we're going to use the contractor results for acceptance, we need to independently verify those results on some sort of frequency. So both, and then it needs to fit into that larger framework of the quality assurance program. So dispute resolution, lab qualifications, personnel qualifications, equipment certification. So those are going to be a big focus on some of the specifications and that are being proposed, and not necessarily for the, say, AASHTO specifications that you'd see for operator and equipment, but more as specifications that a state could utilize and adopt within the larger framework of how they test and operate their quality assurance program. So there's going to need to be a little bit of flexibility there, and because every state has a very different quality assurance program. And so, you know, determining how much is going to be sampled and validated as part of that is going to be a big component of it as well. And as well as the data and analysis side of things. It looks like, so we have we're running short on time. So what I'm going to do, I'm going to skip through a lot of this and find the things that I thought were some of the last things that were most important. So discussed earlier too, if you're looking to utilize multiple intelligent construction technologies, the GPS accuracy is going to play more and more importance. And then depending on how you structure validating contractor results, where if you or again, you're going to need a high accuracy GPS associated with taking the DPS and all their testing. One of the common concerns too is about vendor support and turnaround time for equipment. There was a lot of feeling that if an agency uses the DPS for acceptance, that equipment has become just as important as the roller and your paver and and that the support needs to be real time or parts next day. And so wanted to touch base upon that too, because that's going to help contractors feel that there's less risk on them when something doesn't go quite right, and as well as real-time troubleshooting. And so hopefully we can provide them enough training tools and videos and documents and workbooks that they'll help minimize that the vendor need to do those things. But especially early on, I think there will be a heavy lift there. And so Kyle, we'll relieve the rest, and people can, as they desire, go through these and again try to highlight it in white. But in interest of time, I'll turn back the rest of the time over to you.
Well, thanks a lot, Rob. That was a lot of information and a lot of good stuff. We, I think especially that'll be good to have that presentation posted with the meeting notes, because you hit on a lot of really important things and didn't have time to hit on some other important aspects too. So I think that'll be good. I gave you kind of a yeoman's job to go through, if you guys remember Rob's spreadsheet with all the different comments and challenges and potential solutions that he presented last meeting. That was impressive to be able to get it all summarized in 15 minutes. So we are to the final portion of the agenda, which is discussion, meeting format, feedback, getting an agreement and approximate timing of the next meeting, and then of course adjourning. So unless, are there any specific questions for Rob before we move on? Okay, so just a brief recap of what we tried to accomplish on this meeting. You all probably noticed it was pretty heavy on topics 1 and 2 in terms of, and maybe I'll share my screen here to go through the agenda while I'm talking. So we did cover a lot of topics 1 and 2 here with the data analysis. And what we tried to accomplish with the meeting today was hopefully show how there's use for the technology as a standalone tool, no question about it, and also potential for actually helping with our process control, just using some of that real-time analysis. But then we also wanted to touch on some of the more advanced uses of DPS and how it fits into the big picture, both now and hopefully into the future. The potential of including this technology with some of the other intelligent construction technologies is worth investing in now to get there, I think. So, and we showed some of the stuff we're doing at MnDOT in terms of incorporating DPS with some of the other intelligent construction technologies there. So I thought Fabricio did a great job of really going through some of the critical precision, bias, certification type information we're going to need with this technology to be able to start specifying it for use. We need to have these comparisons with our existing technology that he presented and then Rob highlighted at the end there. Topic 3, we've actually had a formal meeting and an informal meeting on it with the group of people who indicated they're especially interested in that. And Rich Giesel actually has a spec for an airport project that potentially for maybe our next meeting, he'll be able to report on how that's going to be implemented, or maybe even if it can get implemented this year. We weren't able to have Dennis Dvorak, so we didn't spend too much time on that topic today. And then of course at the end, Rob did a great job explaining some of the strengths, weaknesses, opportunities, threats type umbrella topic that we identified as critical for DPS at the end. So I guess one thing that I wanted to discuss with the group is to get feedback, or at least give time here in case anybody wants to comment on trying to change up how we do our format of our meetings for the future. We're kind of just starting this technical working group, and I think now is the time to try different ways of advancing the technology. And I think what we'll plan on moving forward with, unless there's other suggestions, is doing similar to this again, probably towards the end of October, and maybe spending a little bit more time on topics 3 and 4, and less on topics 1 and 2, but do something similar where we have presentations and discussions related to our 4 different umbrella topics. Like I said, maybe towards the end of October. Are there any suggestions to either change the format of how we get together and or timing of when our next meeting should be? Just for context, we're looking at the very end of November for our larger group meeting, which is typically around 100 people or so, versus these kind of more intimate 20-30 people type meetings. So I was thinking maybe towards the end of October would be a good intermediate time to have this technical working group meeting next, before we have the larger group meeting at the very end of November, most likely. So are there any comments on veering differently than the path I just laid out? Suggestions?
I like what you're proposing, Kyle. This is Rich.
Okay, thanks, Rich. Okay, Vanessa, was there any other feedback in terms of the timing and format of the meetings that you'd like from the group, or is that hit on it for you?
Vanessa, you're muted.
Sorry. Sorry about that. Yes, I was just hoping to get feedback from attendees to see if they're happy with the format. By the sounds of it, yes. So I think we'll continue with that. And any kind of concerns for mid to late October call for the next one? I'm not hearing any, so I'm thinking that would be a great time to plan that one for.
Okay, so then I think what we'll end up doing, if you're up for it, Vanessa, is sending out a doodle poll similar to what you did for this one, and then we'll pick a date and time. Did anybody think the 3 hours is too long? Should we try to shorten it up, or are we doing all right with it? We didn't lose anybody, at least officially, so I appreciate and I know this is kind of right smack for the northern states in the middle of construction season, so I appreciate you guys taking time out of your day to join us. Is there any comments in terms of the length of the meeting, 3 hours being okay or not?
There's a comment, 3 hours is good with me, wasn't too long, from Jacob Walker.
Okay, all right. Well, if you think about it and you change your mind, please send us an email. Otherwise, we'll move forward with the proposed schedule. And really thank you guys for taking time out of your day today. It was really useful, I think, for the DPS program. So thanks again, and thank you to CTC for organizing this too.
And apologies about the snafu with Zoom.
Yeah, well, you guys acted quick. You got it figured out, so we're in good shape. All right. Well, you guys have a good rest of your day.
Thank you.
Thank you.
All right. Bye, everyone.